Hey guys, what's up? Welcome to lesson 5 in the Deep Learning with Python course. I'm Max Meadowcroft. This lesson we're going to be going over how to create a neural network as easy as possible to get you guys from 0 to your first running neural network. Again, this course is following the book Deep Learning with Python. Highly recommend reading this book if you want to learn anything about deep learning. And the goal of this lesson is to build the hello world of neural networks. Again, if you guys aren't already in the community that I run for free, you guys should join. It's completely free. There's all the courses I make with extra group projects and resources and more, and also all the notebooks with the code, so you can just run it to follow along with whatever I do. Scan the QR code, school.com/coder to join. Love to have you there. I can help you with anything you need. But yeah, so to get started, first, we're going to go over, in the next few lessons, what we're going to go over is building up an intuition about the notions of deep learning. So some of these basic operations that we're going to be going over throughout the next few lessons are tensors, tensor operations, differentiation, gradient descent, and I'll be trying to explain these in a way that makes sense so that you can grasp them very easily. These are basically just mathematical operations that build deep learning, deep learning is built on top of. So, after the next few lessons, you should have an intuitive understanding of the theory behind deep learning, even if you don't know super technical math stuff around it. And this lesson specifically is just going to get you up and running with a neural network so you can actually train a model how to learn. So how can you run the code? In order to run the code for this course, you can either use Jupyter Notebook or Google Colab. I'm going to be using Google Colab because you don't need a good computer to run it. It's a little easier to set up, and it should be easier to follow along with. So now, going to the code, I need to restart this real quick. Yeah, but anyways, so again, if you're interested in just getting this code file, I'll shoot you a message if you join the community, school.com/coder, and then yeah, I can send it to you, and it will also just be in the course there. So the goal of this code is to get you from 0 to your first neural network as quickly as possible, with at least getting a basic understanding. And you may not understand like really what's happening, but that's okay. It's more so here just for an introduction and to get you some actionable results to get you excited for the rest of this. And upcoming lessons will review each element that we're going over in this example so you can understand it better. But for now, it's just writing the code to just simply get something off the ground and running. And we're going to be using the MNIST dataset, which is a very popular dataset in deep learning, and it consists of 70,000 training and test images of numbers 0 through 9, just randomly assigned throughout, and you can think of solving this as the hello world of deep learning. And yeah, here's some images through the dataset. So now for some basic terms so you can understand what I'm talking about in this lesson and a few other upcoming ones. So in machine learning, a category in a classification problem is called a class. So each of these has a category, which we'll go over what that's called. But basically, in this problem we are solving right now, we're trying to categorize these digits into 0, 1, 2, 3, 4, etc. until 9. And each of those numbers are called a class. Each data point, so each of these images in this example, is called a sample. And the class, so the number associated with a sample, the image of the number, that's called a label in deep learning. So the label for this sample is the class 0. And that's just some basic terminology that deep learning uses so you're familiar with it. This dataset in particular comes preloaded in Keras in the form of a set of 4 NumPy arrays. I'm going to run this real quick to load it. So the first two variables here that we're loading, train images and train labels, are from the training set, and that's the data that the model is going to learn from. The model will then be tested on a test set, test images and test labels, and the images are encoded as NumPy arrays, and the labels are an array of digits 0 through 9. The images and labels have one-to-one correspondence. So for example, the first element in the image is going to be the first label in here. So if it's a 7, it will be a 7. If it's a 5, it will be a 5, etc. So, hold on, let me really quickly just make sure that I get an error here. Okay, cool. I was just testing to make sure that I actually reset it properly. But anyways, here's the training data that we have. Like I said, 60,000 samples, 28 by 28 pixels for the images. And that you can see that here, 60,000 by 28 by 28 is the format that the data's in, which is a 60,000 long array, and then 28 by 28 inside of that, so three-dimensional array. And the length is 60,000 for the number of samples that are there. And here are some of the labels. So for you, as you can see, the first image is label 5, second one 0, third one 4, etc. For the test data, there are 10,000, but everything else aside from that is the same. And as you can see, hold on, I printed out the wrong labels. Let me print out the test ones actually. Yeah, there we go. So as you can see for the test data, the first one's a 7, then a 2, then a 1, etc. So in order to train this bad boy, first we're going to need to feed the neural network the training data, which is train images and train labels. The network will then learn to associate images and labels together and basically transform an input of pixel values to an output of the label that it thinks that the image is to categorize it. Where were we? Finally, we will ask the network to produce predictions for test images, and we can verify these to see how well the network is and potentially retrain if something goes wrong. So the first thing we need to do is build the network. It's okay if you don't understand this step. Here's the code here. Run this block or write it down and then run it on your own. So the building blocks of a neural network are layers, and these are like filters for the data. They're basically a large set of operations that are performed on the data, and the data goes in and comes out in a more useful form. And they extract representations from the data that's fed into them. So in this case, these pixel values are fed into one of these layers, and then from there, the model learns to correlate where certain pixel values are to with which numbers it's likely to be. And layers extract representations. Most of deep learning consists of chaining together a lot of pretty simple actually layers and like operations. And this will implement a form of progressive data distillation. So data will come in the top, very raw, unfiltered, whatever form it's in, so pixel values in this case, and it will go through and get more and more distilled as it goes down these layers, learning more and more higher representations. And it's basically like a sieve for data processing, deep learning models are. And they're made increasingly refined, so whatever we're sieving out is more and more refined as the data goes down. Our model consists of a sequence of 2 dense layers, which are densely connected and also fully connected neural net layers. The second and last layer, right here, is a 10-way softmax classification layer. So we're going to go over what the different activation functions are and the different layers and everything in preceding lessons. But basically all you need to know is that this is the final classification of what the model thinks the input is. So in this case, it's 10 probability scores, and they sum up to 1, and these will represent how likely the model thinks each digit is. So for example, say it gets this input, if it's trained well, it will think that the digit 0 has about a 50% chance, 70% chance of being the digit it's seeing. It depends how well it's trained, and this is a pretty simple model, so the results from my experience aren't always the most consistent, so you might get different results, and we'll go over that a little bit after we train. But basically this last layer just represents the probabilities that the input is each of those labels that we're trying to classify it as. So to make the model ready for training, there's 3 more things we need to set up with it, and this is part of the compilation step. The first of these is an optimizer. Let me make sure, yes, I ran that. And what an optimizer is it's the mechanism for the model to update itself. That should say based, or where was it? So it's the mechanism the model will optimize itself based on the training data it sees in order to improve its performance and actually learn over time. A loss function is how the model is able to measure its performance on the training data. So how it's able to steer itself in the right direction. And then the final one are metrics that we want to monitor during training and testing, so we can see like information that we want to judge how well it's doing. In this case, we're going to use accuracy, or how like correct it is in its classification. So if we run this, that will set up the model and get it ready. The last thing we need to do before training is pre-process the data by reshaping it into the shape that the model expects and scaling it so that all the values are in the 0 to 1 interval. And that's because models learn better that way. We'll go over reasons why in future lessons. Just for now, just pre-process it in this way for this example. So our training images were stored in 60,000 by 28 by 28 of the type unsigned integer 8 with the values between 0 and 255 for brightness values for the pixels. And we're going to transform these into a float 32 array of shape 60,000 and then 28 by 28. So we're just going to flatten those last two dimensions into a single line. So to the model, it's just going to see a long line of values representing an image. Because it doesn't really, like when you think about it, the model doesn't really see any difference between it being, images being certain aspect ratios compared to a long just line of pixels, because it's just taking in basically the values of what each pixel brings. And we're also going to standardize the values between 0 and 1. So here's the way that we can do that. I'm going to run this real quick. So now the next thing we need to do is just train the model using fit to actually allow it to learn. And with this we pass in the number of epochs, which is how many basically times it tries to learn. Batch size of 128, which is groups of the data that it processes at a time. And then down here you can see it actually learning. Each epoch is taking about 6 seconds to complete. And as you can see, the accuracy of how correct it's doing started at 83% about after the first one. And now it's getting to around 97%, which is pretty close to the first time I was writing this, what we got around. And the loss here is also shown, and this is what the model is trying to actually optimize for. And we'll go over the differences between like loss and accuracy and stuff in future lessons. Now that we have a trained model, we can use this to predict the probabilities of new digits. And these are digits that were not part of the training data, like those from the test set. So if I run this, for example, here I'm going to check the first element. I was having this issue, never mind. So as you can see, here is for the first element in the test set. It thinks it is a 7. And these are all the probabilities of each number. So for 0, there's about 7%, 1, 7%, 2, 9%, 3, 11%, etc. And this is just how likely it thinks each of these are. The highest out of these, which we can get like this, is a 7. So that is what it has predicted this image as. And it is 18.8% sure that it is 7, which isn't the most confident, but for categories like this, generally, it won't be ultra confident about it. When I was testing this initially, I got about 15% at index 7. So this is actually a little bit better for that, but we can see how the rest of it does. That is not the right one. There you go. So as you can see, label 0 is actually a 7. We can check label 1 now to see how it does. Thought it was a 2, and it is a 2. Here, let's check this one for label 2 as well. So this is just a little function that is not a, oh, I put the wrong one in here. I was going to say that's not a 2. But yeah, so this is what the model sees, and it predicts a 2 right here. So it's doing pretty good. And here we can see on average how good the model is by checking it with the test data and seeing the accuracy on never before seen data. So if we run this, it will test itself. And we get a test accuracy of 86.9%, which is actually pretty good, especially assuming since there are 10 classes. So if it was just randomly guessing, it would only do about like 10% well on unseen data. But this means that it's actually able to learn some very useful representations because 86.9% is pretty good. This is lower than the training accuracy, though, you might notice, which is 97%. And this gap is an example of overfitting. And what overfitting is, it's the fact that models tend to perform worse on unseen data than training data. And we'll go over more also in detail for what that entails and how to deal with that in the future also. But yeah, thank you guys for watching this lesson. Again, join the community if you're not already, and I'll see you guys in the next lesson.